Welcome to the Insightful Professor. Today we'll take a look at how recursion works. First, we want to consider the general principles of how a subroutine or a function or a method is actually called. What actually happens behind the scenes? We say that a method is implemented as some kind of a subroutine. Typically that's a function, but methods could be implemented perhaps as procedures as well in some languages. When we invoke a method, what we're really doing is calling that subroutine. So we want to recognize the execution flow within a program. If we have one instruction coded, followed by another instruction, followed by another, such as the 3 assignment statements we're showing here, this is what we call a simple sequence. Here we're executing an assignment to X, followed immediately by the execution of an assignment to Y, followed by the execution of an assignment to Z. So we execute the instructions in the order that they're listed. So that's a simple sequence. But when we invoke a subroutine, the subroutine causes the flow of control to kind of suspend this simple sequence and jump to some other location within the program code. And that's what we want to take a look at first, and then we'll consider, with that background information, what happens when we actually invoke a recursive function. So we'll show you how to write recursive functions, and we'll explain the behavior of them within this video. Let's consider a little example so that we can put this idea together. When we call a subroutine, what happens is the runtime environment, so the Java virtual machine, stores the address of the instruction that follows the call to the subroutine. It has to remember that because it is interrupting the sequential execution of the instructions. Let's take a look at what we mean with some code here. In this little code segment, we've made a slight modification. In addition to the 3 assignment statements, we've included a call to a subroutine invoking a method. So here what we have is a simple sequence where we're doing a couple of assignment statements followed by a subroutine call followed by another assignment statement. Now what has to happen in the runtime environment is the system has to know that when it completes execution of an instruction, where in memory does the next instruction reside that must be executed? In a simple sequence, it's relatively straightforward. But when we're dealing with subroutine calls, it's a little bit different. The system has to be aware that it's breaking out of the sequential execution, and it has to kind of put a pointer to say, well, this is where I'm going to go back to. This is the return address. So that would be the case when this method called message is being invoked here. Prior to executing the code stored within this method or this subroutine, the system has to remember and store the return address. It does this by placing this address in what's called a stack frame. So internally in the Java runtime environment, a stack is used to keep track of subroutine calls and return addresses. Take a look at this in a bit more detail. Suppose we examine these instructions and we say we're doing the assignment to variable X. Well, the next instruction to be executed is clearly identified through our simple sequence as the assignment to Y. Then when that instruction is executing, what happens is the next instruction to be executed would be the call to the subroutine, invoking the method called message. Still pretty straightforward in terms of the simple sequence. But when this call to message is actually executed, here's what happens. The system will have to remember the return address, which means the address of the assignment statement assigning the value of some variable to Z. That assignment statement is the next sequential instruction that follows the call to message. So it stores that on the stack so it can remember it. Then it proceeds to make the actual call. Now it goes into the subroutine called message and begins to execute the instructions there in sequence. Keep in mind that when we do something within the method, it could again be a simple assignment statement, but it also could be more complex where it involves the call to yet another message, which means this little diagram that we're representing here, where we're storing information in the stack frame about a return address, this may have to be done multiple times within the method that we called, or the subroutine that we called, in addition to the return address back in the main program. So that means that the stack frames are going to be such that whenever we complete a call to a method, we're going to have the system remove the most recent entry in the stack frame, taking the most recently stored return address, and then go back to that address to resume execution. So when this call to the subroutine called message completes, then that return address is taken from the stack and becomes the address of the next instruction to be executed, which is the assignment to Z. That's how it works in any subroutine call, independent of whether the subroutine is recursive or not. But you need this understanding to gain an appreciation and a further understanding of how recursion operates, because recursion may have a little bit of additional cost associated with it that may not immediately be evident to you if you're not aware of this kind of behavior behind the scenes. When confronted with a problem, we tend to arrive at a solution to the problem by breaking that problem into smaller problems. Each one of these smaller problems solves a portion or a subtask of the original objective. Then when we've solved all of the smaller problems, combining the solutions to the smaller problems results in a solution to the overall problem, the original problem at hand. This is achieved in programming by subroutines. The subroutines implement kind of a modularized approach where each subroutine does a little bit of the solution to the overall problem by solving a specific problem or addressing a specific type of processing. So our discussion of subroutines has basically given us the background that we need to solve a complex problem. Now the question is, what makes a subroutine recursive? That, after all, is the focus of this video. A complete program is broken into many subroutines, and subroutines tend to call other subroutines. That's how we assemble the solution. But an interesting thing about subroutines in a language like Java and many other programming languages is that it's possible for a particular subroutine to call itself. That's what we mean by a recursive subroutine. Effectively, a subroutine that instead of calling a different routine ends up calling itself, invoking itself a second time, a third time, and so forth. Let's look at some ideas as to how this actually works and what the potential benefit is to having recursive subroutines. Here's a simple example, not very useful, but it illustrates the idea of how a function or subroutine can call itself. Here we have a method called message, and it's invoking something called println, which, by the way, is a subroutine, but it's also making a second call. This call is back to itself. We're coming back into message. The problem with this particular example, why it's not useful, other than for demonstration purposes, is that it's never going to end. So this is one of the things that we'll discuss in terms of designing a recursive solution. But the point here is that message is a subroutine that is calling itself. That's the notion of the recursive call. Let's consider a bit more practical example. Here we say that a recursive function has to have some way of controlling the number of recursive calls. We don't want it to go on forever, because remember, with each call, we incur that overhead of creating a stack frame. So if you call yourself and call yourself and call yourself over and over and over again, you're adding all of these stack frames to the internal stack. Eventually, all that memory that is required for the stack frames will exhaust all available memory. So that's not going to be very useful. So what we want to do is have the idea of calling ourselves to satisfy some objective. And we'll explain that in a bit of detail in just a moment. But we also want to do it in a controlled manner. So in this variation of the message method, what we're looking at is a variable called times, which is passed as input as an argument. We accept it and say if times is greater than 0, then we will print out the message, and then the recursive call has to pass a value for times, but notice what it's doing is it's passing a slightly smaller value. It's decrementing the value that it received originally, and now in the recursive call, the value that is passed is a little bit smaller. We've subtracted 1. And we do this over and over until we reach this condition, not being satisfied. That is, the value that we receive as an argument is no longer greater than 0, then we don't execute the instruction here. So the way it works is there's logic contained within the if statement that effectively controls the recursion. That is, whether a recursive call will be made or not is determined by first performing some kind of a test. That test is testing this special condition that we refer to as a base case. If the base case is reached, then we stop the recursive calls. This is implemented in our little example by doing the check with the if, and if the if condition is true, we make the recursive call. Otherwise, we don't. And in this simple example, the recursive calls simply stop, which effectively complete the call to the method. Let's go back and take a closer look here. We say, if this is true, what do? We make a call. We never reach the point down here where we're at the end of the original call. So we make another call. Then if it's still true, we make another call. It's only when we get down to this point here, outside of the if statement, that we actually complete the execution of a call to this method. And that allows us to pop the entry, the return address, from the stack frame and return back to the calling routine. But as long as this condition is true, we're just adding more and more entries to the stack frame and never completing a call. So this is how we actually allow for the recursion to come to a halt. That's quite different than what we saw in the original version of message just a moment ago, where there was no condition. We simply said call message and then call message, never testing for a condition. Let's look at this example in action. Little variation on the code. I've got a file called simplerecursion.java, which effectively does the same thing as the code we just presented in our display. Here we've added a couple of comments, noting that within the main method, what we're doing is signaling that the program execution has begun. This call is made to a method that is recursive. We're going to be calling showMe, passing it a value of 3, and that value of 3 is going to be tested to determine whether a recursive call should be made within the method called showMe. Let's look carefully at the code for showMe. ShowMe is accepting something called times. That would be the value 3 from our initial call. If the value of times is greater than 0, and of course 3 is greater than 0, so for the initial call, this will be true, so we'll perform the operation within the if statement. What do? We put a message out reporting the value of what we received, and we subtract 1 from that and make the recursive call. Notice in the subsequent call, what will happen is that value of 3 becomes 3 minus 1, or 2. 2 is still greater than 0. The next call, 2 minus 1 is 1. 1 is greater than 0. 1 minus 1 is 0. So in that call, that will be the final call, and we'll come down here and complete the execution. Let's look at this in action. So the program started, we passed the value of 3, then a value of 2, then a value of 1. These lines are all displayed as the result of the recursive calls. We've never exited the method called showMe. We entered it 3 times. 1 from the initial call from main, and then 2 times through recursive calls, calling showMe from within showMe. When we passed the value where it became 0, what happened was the if statement failed, so we didn't do any of the body here, and what happened was we completed the call. Then we completed the next call and completed the next call. And that was all accomplished by popping the entry for the return address off the stack frame and going back to where we made the recursive call, and finally where we made the original call back in the main program. And that's where we see the program ending message come out. Let's go back to the main method and show you where that message comes out. It comes out after the original call to showMe. So notice this is not a simple sequence, because we put the message out that says the program was starting, we called showMe, and then we put the message out program ending. But all this other stuff in between was displayed from within showMe, from the original call and from the recursive calls. Okay, that's the idea of how it works. With each recursive call, we passed the current value of times minus 1. The problem got a little bit smaller. We passed a smaller value. And each time the function or showMe was called, it did the same type of processing: test a condition and display a message. Eventually, when the call was made with a value where the if statement did not have a condition that evaluated to true, recursion stopped. And that's where we started backing up. So each time the function is called, there was a new instance of times that was passed, a new version of times parameter. And that was created in memory, and effectively the old version was also added to the stack frame. That's how it was remembered. So that's the general idea of how recursion operates. So let's recap what we've seen thus far. We say that in general, when one function calls another function, the function that makes the call does not end. Its execution is suspended. However, execution will resume within that function when the called function completes its execution. In order to achieve this behavior, the system has to remember this return address, the point at which execution will resume within the calling routine. This is accomplished by using a stack, and placed on the stack is what we call a stack frame or an activation frame. And that's going to record information about that return address. Now, when we talk about recursion, we say that recursion is actually using this same technique as a regular function call. But the motivation for recursion is a little bit different. Recursion, we said, was a technique whereby we could perform some kind of task or perform some operations by performing another set of tasks or operations which were identical in nature but tended to be a bit smaller. That is, we broke the problem down into a slightly smaller problem. And therefore, by solving the smaller problems, we'd end up solving the problem as a whole. So in the message routine that we looked at, each recursive call resulted in the same function or same task being performed. And the same was true when we called showMe in our example. Now, recursion isn't the only way to solve problems. We could do things iteratively. And we've seen that behavior when we introduced loops, where we had a while loop and a for loop and so forth. The idea is we perform an operation, and then we do that operation again and again and again until our goal is achieved. So we have two approaches then to solving problems. We could do things iteratively using loops, or we could do things recursively by having these function calls. Let's take a look at an example. Suppose we wanted to look up the word velarization in a dictionary. Recall that all the words in the dictionary are arranged in order. They're alphabetically arranged. So we have all of the A's, then the B's, and the C's, and so forth. So one approach would be to use something called a sequential search. As we do a sequential search, we would read page 1 and see if we found the word we were looking for. If not, we would proceed to page 2, page 3, and so forth from the start, possibly all the way until the end of the dictionary, until we found our word or found that the word we were looking for was not present within the dictionary. That's a sequential search. An alternative is to take something that would be referred to as a divide and conquer approach. And this is where we can employ a strategy that uses recursion. As an alternative to the sequential search, we could use a binary search. A binary search, we can define its behavior through the concept of recursion. The idea is we would search the dictionary for a word. That's our goal. If the dictionary contains only one page, we scan that page and look for the word on that page, and then we're done. This is the concept of the base case. Alternatively, if we've not achieved the base case, if we've not narrowed it down to a single page, what we do is we begin the process by opening the dictionary to the middle. So we get the center of the dictionary, and because the words are all arranged in alphabetical order, we have 3 possible outcomes. One would be we were fortunate and we found the word we were looking for on the current page that we opened to, right in the middle of the dictionary. But if we didn't find it there, then the word either appears on the pages preceding this middle page or on the pages that follow the middle page. So we have 2 additional searches to perform. But in either event, what we're going to be doing is searching the remaining portion using the same exact approach. That is, doing a binary search. Let's look at it in a little bit more detail. When we divide the dictionary in half, what happens is we use the same strategy to search the remaining half. We identify which half will be searched because all of the words in the dictionary are arranged in order. So once we hit that midpoint and we don't have success, then our word is either in the second half or the first half of the dictionary. Whichever half we target for the remaining search, the other half is eliminated. So we've significantly reduced the size of the problem. That case where we find a single page remaining, that's the base case or the degenerate case. That's where we stop the recursion process. So here's a summary of the search algorithm employing binary search. We're going to search some dictionary, our search space, and the word is the target that we're looking for. Here's the base case, single page. We stop the recursive calls. But if it's not, then notice the recursive calls will say, do the exact same thing, search, but not the entire dictionary, either the first half or the second half, but again, we're passing the same argument to be searched for. So what observations can we make about recursion? The procedure, or the subroutine, calls itself. This is what makes it recursive. Each call to the procedure from within the procedure passes the dictionary that is 1/2 the size of the previous dictionary. On each call, the problem to be solved is the same in nature, but it's smaller. We're getting closer to that base case. And finally, we reach the base case of a single page, we stop the recursive calls, and finally, we complete the search. Now, when you consider a recursive solution to a problem, there are 4 questions to keep in mind. 1, how can you define the problem in terms of a smaller problem of the same type? That is, how can you define T prime in terms of T? You want to do the same thing, but it's going to be on a reduced problem space. How does each recursive call diminish the size of the problem? How do we reduce the size of the problem so that we get a T prime situation? And then what instance of the problem serves as the degenerate or base case? How can we stop the recursive calls? And finally, can we guarantee that as the problem gets smaller and smaller that we ultimately will reach that base case or degenerate case, because that is the key to stopping the whole recursive situation. Remember, when we looked at the first version of message, there was no reduction in the problem. It was just repeatedly calling the subroutine. But when we looked at the second version and the modified version called show me, this is where with each successive call, we passed a smaller integer. And eventually that integer reached the case where we said, we're done. We're not going to make any more calls, the base case. So that's very important to consider these 4 questions in designing a solution that's said to be recursive. Let's look at another example. Now that we've seen the foundation, we've given you a taste of how it works behind the scenes. Let's look at some examples that are a little bit more practical, showing you how recursion works, but also why we might use recursion. Suppose we're given the task of adding a list of numbers, kind of summing a series of numbers. The problem, though, is that we're not allowed to use a loop, and because of that, we can only add 2 numbers. So if you give me 3 numbers, I can only add 2 numbers. After I've added the 2 numbers, I can then add the 3rd number. There's the idea of repeating the addition. Let's look at a set of numbers, 2, 4, 6, 8, 10, 12, 14. This set of numbers is just for illustrative purposes. We're not saying these are the exact numbers that we always want to add, but we want to give this as an example so we can walk through the process. What you want to give attention to as I discuss this procedure here is the process that's involved, not exactly these numbers, because these numbers could be stored in variables where we don't know what the values are, and we don't know how many such values exist. So keep in mind we're using these numbers to illustrate the behavior, but what you want to emphasize or acquire an understanding of here is the process that I'm describing. What we wish to do is to add the first number from the list to the sum of the rest of the series. So effectively, we are extracting the first value and then reducing the problem to a smaller problem. The list of values now to be summed is a little bit shorter than the list we had a moment ago because we've held this value in abeyance. So now what we're doing is saying, take this list, and what we're going to do is add the first number to the sum of the rest. So what we'll do is we'll remove the 4. By removing the 4 from the list, we're delaying the processing of this value. That's one of the things that is accomplished by recursion, to delay the processing of something. Okay, so we repeat this process, and the list gets smaller and smaller. That's where the remaining problem, the identical problem that will be dealt with the recursive call, is of the same nature, but has gotten smaller, until finally we arrive at this base case where the list consists of a single value, and at that point we've completed the recursive calls, and we can start returning values from those recursive calls and performing the actual addition of 2 numbers. And we kind of work backwards at that point. Let's consider how this actually works by looking at this example implemented in Java code. The application to demonstrate the sum series is going to use the exact list of values that we described in the discussion. This list of values has been implemented or stored within an array that we refer to as series. The function to implement the summation is called compute sum and will be passed the array, will also be passed the size or the length of the array, and then will be passed the position of the initial element, right, that first element in the list. Remember that Java uses zero-based indexing or subscripting, so the first element occupies array position 0. The compute sum method is presented here. What we're doing is accepting the array, accepting the length of the array, and then the position of the current element. at the front of the array, at the front of the list. So we test the value of that position at the front of the list and ensure that it is not overrunning the boundary of the array. Remember, the array that contains 7 elements has elements identified as position 0, 1, 2, 3, 4, 5, 6. The last position is always one less than the length of the array. So this effectively becomes the base case, making sure that we're not overrunning the array boundaries. If we have not reached the end of the array, we return the element at the front of the array or at the front of the list plus the output of the recursive call. But notice with the recursive call, we're adjusting the position of the current element. So we're incrementing the position so that if we started with position 0, then on the first recursive call, we have position 1. If we then have position 1 on the next recursive call, we have position 2. So we're always advancing through the array. Notice the array remains the same, and the length of the array, the size of the array remains the same. The thing that we're doing is changing the position of what we consider to be the front of the array, the first element in the list. Notice that if we've reached the base case, we simply return 0. And the significance is that would complete one of these recursive calls. 0 is then added to what we had from the previous call. Therefore, we're not affecting the output in any way. And now we'll run the program. And the sum is 56. And I'll let you confirm that that is indeed the correct answer, but what you want to focus on is the process of recursion. So let me remove this and just bring that code up for you to take a closer look at. And that's the notion of the recursive subroutine. Now, to make it a little clearer, I've modified this application so that what we could do is actually see what's going on. What I'm doing is I'm reporting the position, and I'm calling another subroutine that is going to show you what's in the array so that you can see what's happening as the activity occurs. So this subroutine called showList is simply going to report the content of the array so you can see what's in there. Because we're passing position, each time I call showList, I'm showing you what position currently is as we make our way through the array. So let's fire this one up so we can actually see the behavior of the recursion in a little bit more detail. So what we have is we're starting at position 0. At the front of the list, the element in position 0 is 2. There's the entire list. Then we make the recursive call. 0 plus 1 is 1. So now we're in position 1. At the front of the list is 4. And this is what the list looks like. And you can see that with each recursive call, we are making progress through the list, kind of making the list shorter and shorter, reducing the size of the remaining series of numbers to be summed. Finally, we reach the situation where we are about to do an overflow of the array boundary. That means we're done. There are no more elements. So to avoid that, we stop the recursion. We've reached the base case, and then we start backtracking, and we report what we found. So this little bit of tracking or tracing through recursion, I think, is helpful in understanding the process. So again, this code is available as well in some series too, but it's showing you the details of what's happening. The key to remember is the point I was making a moment ago about the nature of this position. What we're doing is we're advancing through the array or through the list, and what we need to do is do a prefix increment rather than a postfix increment. Otherwise, we would actually overshoot the boundaries of the array. And I'll let you play around with that code and try that out and just confirm your understanding of that behavior. So that hopefully cements the idea together of what we've just looked at with this particular example of sum series. Let's recap what we've seen in terms of a function call and the use of a stack and the stack frames. What happens when any function is called? Well, if the function has formal parameters, things being passed in, they have to be initialized to some values. So the actual values that are used in invoking the function are then assigned to the formal parameters as kind of local variables. The system has to remember where to resume execution when the function completes. So the idea of tracking the values of the formal parameters and remembering those as we suspend execution of the current call and go into another call, and also remembering where we're going to return to when we complete the call, all of that is stored within a stack frame or activation record. And this effectively takes the state of the function and takes a snapshot of that state so it can be remembered and restored when we complete the call and resume execution. So another example is in an application where we have something called countdown, where we're counting backwards. We will take a value that's passed in, check for the base case to see if it's 0. If it is, simply print out the number. If not, we'll show you what the number is, and then make the recursive call to countdown with a value that's a little bit smaller than the value that was passed to us. That's the recursive call. I have the code available. I'm not going to walk through that, but you can run the code and give it a try yourself. So how recursion works, this is a recap of what we've discussed previously in terms of the nature of the stack being a last in, first out type of structure, and that is essential to delaying the processing of something, which is what recursion accomplishes for us, and then basically being able to remember what it is that we delayed the processing for, kind of restoring that state. So the way countdown works is explained here. You can pause the video and take a look at it if you want to examine the code. Now, what about the performance of recursion? Well, recursion has overhead associated with it because of these subprogram calls and the need to put something onto the stack and subsequently to remove something from the stack. That overhead is what adds to the performance cost of using recursion. So the point is, when we use recursion, we don't want to use it just for the sake of using it because it sounds like fun. But the idea is we want to use it because it contributes to a graceful and, say, effective solution to the problem. Keep in mind that it does come with some cost, and that cost is the performance overhead of maintaining the stack. Another example of using recursion to perform some kind of delay of processing is, say, we want to write a string backwards. If you think about what's involved in writing a string backwards, if I wanted to write the string apple in reverse, then I have to delay the writing of the A until I've written the P. And I have to delay the writing of the first P until I've written the second P. And the second P is delayed until we write the L, and so forth. And effectively, we're postponing the processing of all of the leading letters until we found the last letter within the phrase or string that we want to reverse. Then we write that out, and then we go back and get the thing that we delayed the processing of. What did we postpone the processing of? And effectively, that's the concept of the stack coming into play and how recursion solves the problem. So again, we have this available as an application if you'd like to see that in action. Here's a basic idea of the algorithm that's employed. What we're doing is accepting a string, and if the string is empty, well, we don't do anything. That's the base case. But if the string is not empty, we write the last character of the string, and then we call write backwards, and what we're doing is proceeding with the recursive calls to work with something smaller and smaller and smaller. Notice there's an important distinction as to where the recursive call is made. Should we write a character and then make the recursive call, or change the order here and do the recursive call, then write the character? Try that out. It's worth experimenting with to confirm your understanding of the behavior of recursion. So what is it we've talked about in this video? We introduced the concept of recursion. We introduced first how a subroutine is called to prepare you for a better understanding of how recursion operates. A stack frame is used to store the return address and may be used to store other values that constitute the state of the procedure or the function, such as the values of local variables. The characteristics of a recursive call, there were basically 4 questions that we said should be asked in designing a recursive solution. These define the characteristics of recursion. You define a problem in terms of a smaller problem based on the same type of processing. You ensure that each recursive call is going to reduce the size of the problem, so you ultimately arrive at what we call the base case. So you have to identify what that base case is and work toward that with the recursive calls. And finally, we have to ensure that we ultimately do achieve that base case to terminate the recursive calls and complete the overall execution of the function. And we also discussed some possible applications of recursion that involve postponing or delaying the processing of some data. Hopefully you found the video to be useful and informative, and gave you an idea of what recursion is all about. The reason this is important is if you go on and take advanced courses, such as in data structures, what you'll find is that many algorithms are defined recursively, and they could be implemented very simply or very gracefully by implementing them directly using recursion. For example, if you're doing tree traversal, you'll see that recursive algorithms come into play. Binary search, as we talked about, is recursive. So there are many algorithms that have been defined recursively, and hopefully you'll find that understanding recursion gives you a better use of these algorithms, better understanding of them. So if you found the video informative, considering giving a thumbs up, and also make any comments to make suggestions as to how we might be able to improve videos in the future. And also consider subscribing to the channel. There's no cost for it, and it'll give you a chance to be notified when we add future videos. And once again, thanks for watching.